In this video, we're going to be taking a look at that same parallel plate capacitor, but we're going to approach it from a slightly different angle. We're now going to solve this as a boundary value problem. And so what that means is instead of assuming a charge on each plate, we're going to assume some voltage across the capacitor. So you can see I've got our same capacitor that we considered in the previous video, our two metal plates on either side of our dielectric. We have the bottom plate is being defined as x equals 0, and the top is x equals d, such that we have a total dielectric thickness of d. So let's go ahead and assume on the top here we have some voltage V0, which means our bottom plate is going to be at ground potential. So because we're only going to have variations in one dimension, we're going to be solving a one-dimensional boundary value problem. So one-dimensional, and of course we can have higher dimensional boundary value problems, but for the purposes of this class we're not going to consider that. So one-dimensional boundary value problem, and our boundary conditions, so BC, are going to be at our bottom plate, so x equals 0, we have a 0 voltage, and at our top plate, which is x equals d, we're going to have a voltage V0. So when we go to solve this boundary value problem, of course we want to choose our Laplace or our Poisson equation. In this case, we're going to use our Laplace equation because we don't have any free charge density in that volume between the two. So we have that the second derivative of voltage with respect to x squared is equal to 0. And again, because we only have the one dimension, that's why we have the relatively simple sort of just our differential with respect to x, and there's no y or z dependence. So here, all we need to do is integrate this equation twice. So integrating twice, so we integrate the first time and we're going to get one constant. We integrate the second time, it's that constant times x plus a second constant. So we end up with v equals ax plus b, where our a and b are constants of integration. So what we want to do now is we want to use our boundary value, or our boundary conditions, to solve for our integration constants. So our integration constants, which again are a and b. So let's go ahead and start at that bottom plate. So we said at the bottom plate, x equals 0, and we know our potential at that point is 0. So plugging it into our expression here, and again, we're considering this boundary condition, we have a times 0, because our x is 0 at the bottom plate, plus b. And so of course what this tells us is that our b is equal to 0. Let's consider our second boundary condition right here. So now we're considering x equals d, and we're saying this is equal to v0. So we plug into this equation, and we have a times d, and we just found out our b is 0, so all we have to do now is solve for the a, and we see that that is v0 over d. Plugging those back into our expression here, we get a final voltage expression. So we get that our v is equal to v0 over d times x. Okay, so our approach now is we want to find the charge on our capacitor plates using this voltage expression. So find our Q on plates, and once we have that, we can solve for our capacitance as Q divided by V0. And so this sort of emphasizes the difference in approach. So remember in the previous video, we had assumed some Q, and then we used that expression to solve for V0. And here we started by assuming some V0, and now we're going to use that to solve for Q. So again, slightly different approach, but same basic idea. All right, so how do we get our Q then? So it should be mentioned first that what Q are we even talking about? Well, we're talking about Q on the plates, and so the highlighter is not going to work here for whatever reason, but we want the Q that is on the plate sort of at this metal dielectric interface specifically. And so we're looking for some charge density rho sub s. So we can say that the overall Q on the plates is just going to be the surface integral of that charge density rho sub s. So we have the integral over the surface of rho s ds. So now our problem simplifies to how do we get this rho s from our voltage expression. So how to get rho s from V? Because again, we have this expression for V, so how do we utilize that? So it's actually a couple steps, and we're going to be using equations from our previous unit. We know for a perfect conductor, we're not going to have any electric field in the conductor, and that our external fields are going to be perpendicular. So for a conductor then, we have that rho s is equal to dN. And so this was the result that we got when we looked at our dielectric conductor boundary condition in the previous unit. Now, of course, we can write this dN as some general d dot the unit normal vector. So if we're talking about unit normal vectors, let's come back up here to our figure for a second. And we're actually going to define these unit normal vectors pretty much the same way as we did in the previous video. So let me go ahead and actually get rid of these. So if we're talking about this top plate, we're going to have a unit vector in this direction. And so we can see this is equal to negative x. And for the bottom plate, our unit vector is going to be upward. So that's going to be a positive x direction. Okay, so keeping that in mind for a little bit later on. So we know we could get this rho of s from d. Well, we still need to figure out how to get d from our voltage expression. Well, of course, we know that our d is simply equal to epsilon times our electric field. So now we just need to figure out how to get our electric field from our voltage. Again, we go back to previous expressions and we say our electric field we know is negative gradient of our voltage. So now it's just a matter of sort of working our way through this so we can find our voltage, or from our voltage we can find E, from E we can find D, from D we can find rho s, and from rho s ultimately we can find Q, and then finally our capacitance. So let's go ahead and start by finding our electric field. So we know our electric field is equal to negative del of V, and so in general that's going to be negative partial of V with respect to x in our x direction, plus partial of V with respect to y in our y direction, plus partial of V with respect to z in our z direction, because we're in Cartesian coordinates. Now, of course, these last two terms are going to go to 0 in this case because we only have x dependence in this voltage expression. And so that partial derivative just becomes a full derivative. Taking that, we can see the result is just going to be V naught over D. So this is going to give us an electric field of negative V naught over D in the x direction. Okay, so now we want to consider sort of our lower and upper plates separately when we do this expression here to get our rho of s. So first, let's take a look at our lower plate. So for our lower plate, again, I'm going to sort of combine sort of these two steps here, going from E to rho of s directly. I can say my rho of s is equal to epsilon times my E, which was negative V naught over D in the U of x direction. And I want to dot that with the unit normal to get my rho of s. So I'm going to dot that with U of x because for the bottom plate, remember we had said the unit normal was in the x direction. Okay, so of course U of x dot U of x is just going to be 1, and so we get negative epsilon V naught over D. So then if we integrate over the surface, if we assume we still have surface area S, that's going to give us some total Q, which is just equal to rho s times S. So that's going to be negative epsilon V naught times S divided by D. So now let's talk about the upper plate. So for our upper plate, same basic approach. So we have rho of S is equal to epsilon times E, which is negative V naught over D in our x direction. The one difference is that now our unit normal vector is not going to be in the x direction, but in the negative x direction. So we come back down here, and now we're going to dot this with negative U of x. And so U of x dot negative U of x is going to be negative 1. The negative sign is going to cancel out with this negative sign, and we end up with a positive epsilon V naught over D. So again, if we integrate over the surface area, it's just going to be Q equals epsilon V naught S over D. So as we would have expected, we have equal and opposite charge. So these two charges on our upper and lower plate are the same magnitude, just a different sign. So finally, we can come back and we can solve for our capacitance. So we can say our capacitance is the magnitude of that charge on each plate divided by V naught. And so we see if we were to take, for instance, this equation here and divide by V naught, we're just canceling out here. So if we do this, we get our V naught canceling out, and so we get epsilon times S divided by D, which is of course the same expression that we found previously, as we would expect.